9.8 Cell potential and free energy. Our outcome is I can explain whether an electrochemical cell is thermodynamically favored based on its standard cell potential and the constituent half reactions within the cell. So, in other words, we want to be able to predict whether a process is favored thermodynamically, if it is spontaneous, based on what the cell potential and what the cell is made of. So we want to be able to look at a cell and look at its components and know whether or not that cell will function as it is shown spontaneously. So some important terms, constants, and units that you should be familiar with. First is the Coulomb. So we've already talked about Coulombic attraction. That's the attraction between particles due to opposite charges. So a Coulomb is the unit that we use to describe charge. The Faraday is the amount of charge that's present on 1 mole of electrons. So you should think of this as a conversion factor. We can convert between moles of electrons and coulombs of charge. And that's really important because we use cell potential to do work, to produce a voltage. We want to use the flow of the current of electrons to do some kind of work here. So the amount of work we're going to be able to do depends on how many coulombs of charge are being transferred. A volt is 1 joule of work per coulomb of charge transferred. So this is why voltage is considered an intensive property. Whenever we balance our chemical equations with cell potentials, we might need to double an equation or multiply it by some factor to ensure that we have the same number of electrons. But we never multiply the actual voltage by that number, and it's because it depends on the amount of charge that is transferred, not how many times the reaction occurs. Now, we want to use the current from the flow of electrons to do some kind of work, so something like run a motor. So we need to take those electrons, and they are being pushed through a wire. So there's going to be some resistance to that flow, and some of that energy is going to be lost as heat. So the actual amount of work that a cell can do is going to be less than the calculated value. And so these two equations that are on the screen are really both the same equation. They're just rearranged differently. So here we have a galvanic cell made from copper and gold, and we want to know what the maximum possible voltage is for this cell. So we're just going to calculate the voltage on this cell from these two half reactions. So first we need to look at these two reactions, and they are both written as reduction. So we're going from copper plus 2 to copper metal, copper 0. And gold plus 3 to gold 0. So one of these equations is going to need to be flipped around because a reduction reaction needs to be paired with a oxidation reaction. So the cell potential that is larger, more positive, that is going to run as is, as reduction. So I'm going to need to flip my copper equation to run as my oxidation. Now, because I'm flipping the direction of the reaction, I'm also going to flip the sign on E cell. So now we have negative 0.34 volts here. So the gold equation is going to stay as is because the cell potential is larger for the gold reaction here. That one will run as reduction. So that's my reduction, that's my oxidation. So if you look at the number of electrons here I'm producing 2, and here I'm consuming 3. So we need to make those numbers of electrons equal. So for 2 and 3, I'm going to aim for 6 here. So I'm going to multiply my top equation by 3 and my bottom equation by 2. Now notice that I'm not going to do anything to my voltage for each half reaction. That's what I meant earlier whenever I said that voltage was an intensive property. So it doesn't matter that this reaction happens 3 times or this reaction happens twice. The potential that is produced is the same in either way because it depends on how many coulombs of charge are transferred. So now I want to combine and cancel. So I'm going to distribute the 3, distribute the 2, combine and cancel. So I end up with this for my balanced equation here after distributing and canceling. And I got to this equation by combining these 2 half reactions. So I'm going to get this voltage by combining those 2 half cell voltages. So this is the amount of voltage that we should be able to achieve here. Now we want to calculate the theoretical amount of electrical work and the actual amount of electrical work done by the cell. So this particular cell transferred 1.50 moles of electrons at an average potential of 1.08 volts. So we're going to use this equation here. Work is equal to negative Q times E max. And notice those both have Q in them. So Q is our charge, our coulombs. So I can calculate that because we've transferred 1.5 moles of electrons. So I'm using that Faraday constant to convert from moles of electrons into coulombs of charge. So once I get that answer, I just need to multiply that by the maximum voltage and the actual voltage of the cell. So we previously calculated that the voltage was 1.16 joules per coulomb. So when I multiply that by coulombs, that's going to give me joules. So remember that a joule per coulomb is the same thing as a volt. So I'm going to do this again, but this time I'm going to multiply by the average potential that the cell ran at here. So that's 1.08. So that gives me the actual amount of work done by the cell. And notice here that there is a negative sign in front of work, and that's because the cell is doing the work. So that negative sign is associated with that. So we see that my maximum work is one number, and my actual work is a different number. And that's because some of that energy is going to get lost as heat and not be converted into work. So efficiency is really just a ratio that tells you how much of the maximum work was actually achieved here. So I'm just going to take my experimental value and divide it by my maximum value, and I get efficiency of about 0.93. So we're losing about 7% of the energy that we could be using to do work. So how does electrical work relate to free energy? So remember that free energy is delta G, and whenever we have a negative delta G, that indicates that that process is spontaneous, or we could also say thermodynamically favored. Both of those mean the same thing here. So how does electrical work relate to this negative delta G? So the change in free energy is equal to the maximum amount of work obtainable. So free energy is just energy that is available to do work. So it makes sense that the maximum amount of work is going to be defined by the free energy. So the maximum amount of work is just basically equal to delta G. Now, when a cell has a positive voltage, delta G is negative, and the reaction will be spontaneous. So that leads us to another equation here. Delta G is equal to NF times E cell. So N here is going to be the number of moles of electrons from our balanced equation. F is again that Faraday constant. And E cell is the voltage or potential that we can generate from that cell. So anytime that we have a positive voltage, we're going to get a negative delta G, which is going to be spontaneous. If you're solving and you get a negative voltage, what that means is that you are probably going to need to switch your cathode and anode so that the electrons will flow in the opposite direction, which would be spontaneous. A dead battery is a battery that has gone to equilibrium. So the battery components end up with the same value for free energy. It's at equilibrium. So that means that delta G is 0. So that would be non-spontaneous. No reaction would occur, and there would be no flow of electrons. So if you have a rechargeable battery, what you can do is plug that into a power source, and that's going to force those electrons to flow in the opposite direction, recharging your battery. There's another type of electrochemical cell that's called a concentration cell. And the idea here is that both cells would have the same components, just in different concentrations. So the difference in concentration is going to produce a cell potential. One of those cells will have a stronger pull on electrons than the other. And that makes sense that that would be the one that's more concentrated. So the voltages here are typically going to be small because there's not going to be a big difference in cell potential. Now, a very useful equation here is going to be the Nernst equation. So this allows you to calculate the voltage, the cell potential, when some or all components are not in their standard states. So standard state means 1 atmosphere pressure for gases, it means 25 degrees Celsius, and it means that solutions are in 1 molar. So you'll most often encounter this whenever we're looking at a concentration cell where we have different concentrations of components. But you can also use it to calculate for any time that you're not at standard states. So in this equation, notice that we have E cell and E naught cell. So E cell is going to be my non-standard value, and E naught cell is the standard voltage. So if you look up your half reactions and flip one of them and balance your reaction and combine voltages, those are going to be those standard voltages. E cell is just whatever the voltage is at those non-standard conditions. So in this equation here, we have our standard state voltage, and then we are going to subtract this term here. So we can think of this as like a correction factor to deal with the fact that we're not at standard state. So in this equation, R is the gas law constant, T is the temperature in Kelvin, N is the moles of electrons, and F is our Faraday. Now notice that we have a natural log of Q here. So Q is the reaction quotient. It is calculated in the exact same way as K, our equilibrium constant. If we have a reaction that's not at equilibrium, we can predict which way it's going to change to get to equilibrium. So that's why Q is involved here, because if we favor the forward reaction, we're going to end up with a higher voltage than what we would predict, whereas if we favor the reverse reaction, we would end up with a lower voltage than we would predict. Now, another useful thing to do is to combine the constants together here. So at 25 degrees Celsius, this number here is equal to RT over F. So at 25 degrees, R and F are both constants, so we can multiply those together just to kind of simplify that equation sum. So these are both the same equation, it's just that here we've combined some constants into a single constant. So take a few minutes here to go ahead and write a summary of your notes here. So some guiding topics, you can talk about finding efficiency, electrical work and free energy relationship, how do those relate, and any of those important equations and conversion factors. Here are some reflection questions to answer. So what values of E cell are going to be thermodynamically favored? How does this relate to delta G? And explain how to calculate E cell from half reactions.